In this video, we're going to talk about bases in the singular value decomposition and computational tools to help us find a singular value decomp. So let's say that A is an m by n matrix, and it has R non-zero singular values. So then when we write A in terms of its singular value decomposition as U sigma V transpose, we get the following. We get something of this form. So remember that this first vector right here, this is U1, the first column vector of the matrix U. And then we go like that up until the rth column vector, so UR. So those first R column vectors, so those are going to correspond to the R non-zero singular values. They can be written in this form as 1 over sigma I times A times VI. Okay, and then these other column vectors in U, we'll talk about how to find those a little bit later in this video. And then this matrix in the middle, this is the matrix sigma. And with this matrix sigma, the number of non-zero singular values, that is equal to the rank of A. So that we had seen previously in an earlier video. This was a theorem that we showed. So it turns out that this singular value decomposition tells me important information about the bases of A. And what I mean by that is things like the basis for the column space of A and the null space of A and so on. Okay, so what I'm going to do is I'm going to order the thought process in which I write this stuff down. So the first thing I did was I wrote down what sigma was telling us. So the number of non-zero singular values tells us the rank of the matrix. So that's sort of the first thing that I've talked about. So we've seen in a previous video that these first R columns in the matrix U, they form an orthonormal basis for the column space. Right, because we showed in a previous video that AV1 up until AVR were an orthogonal basis for the column space of A. And then when you multiply them by 1 over the corresponding singular value, that will normalize them. So it becomes an orthonormal basis. So this we had seen in a previous video. Okay, so this is my second thought process. The second step in my thought process. Okay, so what about these remaining columns in U? So these other columns in U, well, collectively with these first R columns, they're all supposed to be orthonormal. So these specifically, they're going to form an orthonormal, I'll just abbreviate, orthonormal basis for, and these vectors UR plus 1 up until UM, they need to be orthogonal to the first R vectors. In other words, they need to be orthogonal to everything that's in the column space of A. So they are going to form an orthonormal basis for column space of A perp its orthogonal complement. And we've seen before that column space of A perp is the null space of A transpose. All right, so that is the third thing that we've reasoned out now. So now let's talk about the vectors in V. So notice that this is V transpose. So it's important here that this is being transposed, because in the singular value decomposition, V is supposed to be transposed. But the way I'm writing these columns right now, so V1, VR, up until, technically all the way up until Vn, these are all the columns in V. All right, so where do these V's come from? So remember, these are the eigenvectors of the matrix A transpose times A. So that's what they are. And the first R of them, V1 up to VR, they have non-zero eigenvalues. So the first R of them, V1 up to VR, they corresponded to non-zero eigenvalues, and therefore these non-zero singular values. So sigma 1 up to sigma r, these were all the non-zero singular values. All right, so that means is the last n minus r vectors here. So starting with vr plus 1 up until vn, they all correspond to the eigenvalue 0. So they form an orthonormal basis for the eigenspace corresponding to the eigenvalue 0. So for E naught, so they correspond to lambda equals 0 for the matrix A transpose times A. Okay, so the eigenspace that corresponds to 0 is a null space. It's the null space of, so remember, we were finding the eigenvectors and the eigenvalues of A transpose times A. So this is the null space of A transpose times A. Okay, but in a previous homework, we showed that the null space of A transpose A was equal to the null space of A. So this was a previous homework. So in an old homework, we showed this. So VR plus 1 up until Vn, they are actually an orthonormal basis for the null space of A. All right. So that is step 4 in my thought process here. So finally, that leaves us with V1 up until VR. So they are also collectively orthonormal. So these are going to be orthonormal. They're going to form an orthonormal basis for the orthogonal complement of the null space, because these all need to be orthogonal to these vectors that were in the null space of A. So they're going to form an orthonormal basis for the null space of A perp. But the null space of A perp, that is, we've seen before, that is the row space of A. That is the row space of A. And the rows of A are the columns of A transpose. So row space of A is the same thing as the column space of A transpose. And that is step 5 in my thought process. So let's look at an example. So it turns out that the matrix A, which I've written here, has the following singular value decomposition. So it turns out this is U, this sort of narrow matrix in the middle, this is sigma, and this matrix at the end, this is V transpose. So what I want to do now is I want to write down all of these fundamental spaces, like the column space and the null space of A transpose and the row space of A, and so on. Okay, so let's see if we can write down all of these. So let's start with a column space of A, and let's write down what this equals. So first notice that if we look at the matrix sigma, there is one non-zero singular value. So there is one non-zero sigma I. That means the rank of the matrix should be 1. However many non-zero singular values we have, that's what the rank of the matrix A is. Okay, so that means the column space of A should have 1 vector in its basis, because the rank is 1. And if we look at our work above, that just means that R here, R is 1. There's 1 non-zero singular value. So that means the first, if I want to find a basis for the column space of A, I'm supposed to look at these first R columns in U. In this case, it's the first 1 column of U, this column right here. That's going to be a basis for the column space. So let's write that down. So we have 1/3, -2/3, and 2/3. That is forming a basis for the column space of A. So the column space of A is the span of this vector. So the column space of A is the span of that vector. So let's also highlight this in yellow so I can remember later that that's what it corresponded to in my matrix here. All right, so next let's do null space of A transpose. So null space of A transpose, that's the stuff that was orthogonal to the column space of A. And we've seen here that these are the last columns of the matrix U after we do the first R. So in our example, so here we go. This is where we'd begin, and we'd go all the way until the end. And they're going to be a basis, an orthonormal basis for the null space of A transpose. All right, so let's write those down. So null space of A transpose. So we have 2 over root 5, 1 over root 5, 0, and then 2 over root 45, 4 over root 45, 5 over root 45. And then we need to take the span of these. Let me move this over so we can write span. So let's move this over. And then let's write the word span. All right, so that is the null space of A transpose. So let's highlight these as well. So next, let's do the row space, which is the same thing as the column space of A transpose. What is this going to be the span of? So if we look at our work above, the row space, an orthonormal basis for the row space is the first R columns of the matrix V. But one thing we need to be careful about is, notice that when we see our singular value decomposition written, this matrix right here, this is V transpose. It's not V. And I need to figure out what the first R columns are in V, not V transpose. So the rows of V transpose are going to be the columns of V. So because R is 1, there's one non-zero singular value, an orthonormal basis for the row space is it's just going to contain the first column of the matrix V. But the first column of V is the first row of V transpose. So I need to be writing down the first row of V transpose. So that is 1 root 2, and then negative 1 over root 2. So I'm writing that first row, but as a column vector. Okay, so this is a basis for the row space. So the row space is the span of that vector, and that we saw in the first row of V. So that's a super important point, that we remember that this is V transpose, not V. So when we write down what the row space is, we had to look at the rows of V transpose, because they correspond to the columns of V. All right, so finally we need to describe the null space. So the null space of A is going to be the span of the remaining columns of the matrix V. But those remaining columns of the matrix V are going to be the remaining rows of V transpose. Okay, so that means here is the remaining row of V transpose. That corresponds to a column of V. So that's what's going to go for the null space. The null space is going to be the span of that remaining row of V transpose. 1 root 2 with 1 root 2. I'm writing that row as a column vector. Okay, so let's highlight that here as well. All right, so we've described all of them. So giving a summary of what we've shown now, one of the reasons why the singular value decomposition is really powerful is because it uncovers within U and V orthonormal bases for the column space of A and the null space of A transpose in the matrix U, and for the row space and the null space in the matrix V. So I want to end this video by mentioning a couple of computational tools that are useful when we find singular value decompositions. So the first is, if we want to find the columns in U after the first R, so if we want to find UR plus 1 up until UM, we need to get an orthonormal basis for the null space of A transpose. And that's the same thing as column space of A perp. So we'll talk in the next video about 2 ways to do this, but the overall problem that we need to do is we need to find the null space of A transpose. Specifically, we're going to find a basis for the null space of A transpose. And when we find a basis for this thing, it's not necessarily going to be orthogonal right away. And it's definitely not necessarily going to be orthonormal right away. So we're going to have to do Gram-Schmidt possibly. And then after doing Gram-Schmidt to get an orthogonal basis, then we're going to have to normalize. Okay. So computational tool part 2, or computational tool number 2 is that A transpose A and A times A transpose have the same non-zero eigenvalues. So this is this thing that I just underlined here. This is a good exercise to try to show why. This is a really good problem. Okay, but so I'm not going to show that in the video here. Instead, I want to talk about, well, why is this useful? So if we want to get the singular values, sigma I, we can use the non-zero eigenvalues of A times A transpose if that ends up being easier. So let's look at an example. So let's say A was this matrix right here. So this is a 2x4 matrix. So let's look at both A transpose A and A times A transpose to see which one seems like it would be easier in terms of finding our eigenvalues. All right, so I've gone ahead and done the computation of figuring out what A transpose A is and what A times A transpose is. So notice that A transpose times A, this is a 4x4. This is a 4x4 matrix. And that's going to be hard to find the eigenvalues and the eigenvectors of. A times A transpose, on the other hand, this ended up being a 2x2 matrix. And that's easier to find the eigenvalues and the eigenvectors of. All right. So based off of that result we just noticed that we observed about this computational tool number 2, if we want to write down the eigenvalues of A transpose A, it's going to share the same non-zero eigenvalues that A times A transpose has. And with A times A transpose, we can actually see what its eigenvalues are just by looking at it, because this is a triangular matrix. In fact, it's a diagonal matrix. So the eigenvalues are just along the diagonal. So 6 and 6, we have a repeated eigenvalue. Those are both also going to be eigenvalues of A transpose A. Okay, so A transpose A and A times A transpose have the same non-zero eigenvalues. In this case, it's 6 and 6. So what that means is we've now identified all the non-zero eigenvalues of A transpose A, which means all the other eigenvalues must be 0. And the other eigenvalues are then 0. So how many other eigenvalues is A transpose A going to have? Well, it's a 4x4 matrix. So counting repeats, it's going to have 4 eigenvalues. So that means the other two, lambda 3 and lambda 4, are both 0. Okay, so this comment right here is how we determined that lambda 3 and lambda 4 were both 0. So just to reiterate one more time, this was useful because if we tried to find the eigenvalues of A transpose A directly, we'd end up having to find the eigenvalues of this 4x4 matrix, and that was a lot more complicated. It looks a lot harder. It looks harder to find the eigenvalues of this matrix and easier to find the eigenvalues of this matrix. Easier to find the eigenvalues of this matrix. And our computational tool says it's totally fine to instead get the eigenvalues of A times A transpose if that's easier, because the non-zero eigenvalues are going to match up.